Spontaneity lets us determine if a reaction's actually going to go or if it's not going to go without outside influence. Now, when we look at enthalpy at this level, studying enthalpy it's just the beginning. We're just going to do a brief cursory understanding of what spontaneity is here. If you're taking a second semester general chemistry class, you're going to do another chapter on thermodynamics where you will go into the second and third laws of thermodynamics, and you will do a deeper dive into spontaneity. But I don't want to leave you on this subject without understanding that the measure of a reaction is more than just its delta H. And that's why I've pointed out, when we look at the exothermic versus endothermic, a lot of times endothermic reactions wind up being non-spontaneous. However, there's things like those cold packs that are spontaneous even though they're endothermic. And that's because there's more than just delta H to consider when we're looking at the thermodynamics of a reaction. All right. And so when we start thinking about chemical spontaneity, if we are giving off heat, we expect those to be spontaneous, and those that absorb heat, our endothermic ones, to require energy in order to happen. Okay, but what ends up occurring is something a little bit crazier. Okay, so sometimes we get things that are spontaneous despite the fact that they are endothermic. So this reaction right here, this one's really cool. But you take solid barium hydroxide octahydrate and some ammonium chloride, and you mix them together, you get this mixture of water, ammonia, and barium chloride. This reaction is so incredibly endothermic that if you have a plank of wood and you have a little bit of water and you put the beaker that you're doing this reaction on top of it and you do the reaction, it causes that little bit of water underneath it to freeze, and then it sticks to the bottom of the plank. So it looks like this. So this has a delta H of reaction that is 62.3 kilojoules. That's positive. Okay, so this is an endothermic reaction. Yet it is spontaneous. So the this one's ammonium nitrate instead of ammonium chloride, but it's the same sort of a thing. Okay, so here I've got the barium nitrate. Now barium nitrate, if I have water around, is not going to be an intact barium nitrate crystal. It's going to be barium ions and nitrate ions. So think about this. What is more orderly? A solid that's all rigid and held together, or a gas or an aqueous solution, or even just a liquid? The more orderly is going to be the solid. And so if you look at this reaction, we have two solids that result in a bunch of ions floating around solution, either some aqueous ammonia or even potentially some ammonia gas giving off, and a whole bunch of water. So we go from two very highly ordered systems to something that is very disordered, which brings in another variable that's very important in thermodynamics, which is entropy. Okay, so entropy is looking at the amount of disorder, the amount of randomness in a system. Systems want to go to that state of lower energy. So the lower energy system is the one that is all chaotic and insane. And so what's interesting about this is the highest entropy is the most disordered. So when your room gets messy, that's actually just obeying the laws of thermodynamics. Because if you think about it, what takes more effort? What takes more energy? Putting things away neatly or just dropping things wherever they land? Well, obviously putting things away neatly takes more energy. And so that's a state of higher energy. The state of lower energy is just the mass chaos. And so that's why it takes a lot of effort to keep up with cleaning and make sure that things stay neat, is because the laws of the universe, okay, this has to do with the second and third laws of thermodynamics. These are just saying, like, look, chaos is the way it's supposed to be. We don't want to be all orderly because that takes energy. All right, and so the more positive entropy is the greater disorder. So S is the variable that we use for entropy. Okay, but that's not even the entire picture of all of this. What finally determines the spontaneity of a reaction is this guy right here. This is delta G. This is our Gibbs free energy. This is going to let us know, first of all, if a reaction is spontaneous, and second of all, what temperature we need to be at in order for that reaction to be spontaneous. Because sometimes you can be spontaneous at one temperature and non-spontaneous at another temperature. All right. And so again, the spontaneity, we're looking at things that I don't have to give it any outward influence. It just happens. I drop the things together and it just happens. And so our Gibbs free energy is what defines whether or not something is spontaneous. All right. And so we get this right here. This delta G is equal to delta H minus T delta S. For our first semester course, we don't actually do anything with this Gibbs free energy equation. All right, this is something you will do in thermodynamics when you take a second semester course. But I point this stuff out here because one, I want you to know that Gibbs free energy exists, and two, I think entropy is really cool, and so I want to make sure that I at least touch on entropy and explain to you what entropy is. And I do expect my students to know that delta G stands for Gibbs free energy and is what is the defining factor for the spontaneity of a reaction. And I expect my students to know that delta S is dealing with the change in entropy, and we want to be more disordered. I am going to expect that of you, that you understand that we want to go to the state of lowest energy, and the lowest energy state is the craziest, most disordered state possible. And so there's a lot of things that go into the spontaneity of a reaction, the enthalpy, the temperature, and the entropy. And so if you have opposite signs for your enthalpy and your entropy, you can predict your delta G no matter what. But if delta H and delta S have the same sign, then the spontaneity of the reaction becomes temperature dependent. And so you will cover that in more detail when you go into a second semester general chemistry course. And if you end up loving chemistry and majoring in chemistry, then you might even take an entire course just on thermodynamics. Personally, I know if you're watching this, you're probably rolling your eyes because I sound really excited. I'm an electrochemist by trade. That's what I was trained as, but to understand electrochemistry, you have to understand thermodynamics. And so really my areas where I get the most excited are electrochem and thermodynamics. Thermo is fascinating. Thermo defines what we see in the universe and why we see what we see and how all that goes together. And so thermo is super, super cool. And so I want to make sure that I am leaving you at this chapter understanding that there is more to the story, okay? This is like, just the first chapter of thermo, and we're just pausing here so that you can learn some more stuff before we then start expanding and moving into more of what happens in thermo. And really, even in Gen Chem, you're only going to get to like chapter 2, maybe chapter 3 of thermo. There's a lot more to it. So anyway, I leave you with this. The spontaneity of a reaction depends on the delta G, and it requires both the enthalpy and the entropy contribution. And my house follows the laws of thermodynamics. I need to clean and organize things. That is definitely not my strongest suit. All right, anyway, there you go, thermo.